Fractional Chern Insulators, FCIs, are fascinating quantum materials that extend the concept of traditional Chern insulators, which behave like electronic highways with unique lanes for electric currents. Imagine a Chern insulator as a perfectly designed multi-lane highway where cars, electrons, travel without getting mixed up, thanks to special signs, topological properties, that keep them on track. Now picture this highway operating in a more exotic way, where cars not only follow these unique lanes but also interact with each other in complex, coordinated patterns, akin to a well-synchronized dance routine on a crowded dance floor. Here, each dancer moves precisely without collisions, forming intricate patterns. FCIs emerge when electrons in such systems form quasi-particles that carry only a fraction of the electron's charge, leading to remarkable phenomena like fractional quantum Hall states on a lattice. An everyday analogy is like having water molecules arrange themselves into precise, repeating patterns to create ice crystals, but with the added twist that each molecule behaves in a fractionated, unusual manner. Another example is thinking of FCIs as a group of musicians in an orchestra, where instead of each musician playing individually, they form small ensembles that play in perfect harmony, creating richer and more complex music. Similarly, in FCIs, electrons interact in such a coordinated way that they form new stable states with unique properties. This ability to create stable fractional charge carriers is crucial for developing robust quantum bits, qubits, in quantum computing. Much like a well-coordinated team performing complex tasks more reliably than individuals working alone. FCIs open new doors in quantum computing and condensed matter physics by leveraging these intricate, coordinated behaviors to create highly stable and exotic states of matter. Now, imagine a coffee mug. These objects seem different, but in topology, we look beyond their everyday appearances. We focus on their fundamental properties, properties that remain unchanged even if we stretch, twist, or bend them. A donut, with its single hole, is topologically equivalent to a coffee mug. Both have one hole, a fundamental property. This concept of topology, where shape takes a backseat to fundamental properties, finds its way into the quantum world. Welcome to the fascinating realm of topological phases of matter. Here, materials exhibit exotic properties governed by their topological order, not just their internal structure. These properties, like the hole in our donut, remain robust even in the face of disturbances. This stability holds immense potential for revolutionary technologies, including fault-tolerant quantum computers. Navigating the quantum road topological insulators. Imagine a highway with a curious feature lanes of traffic flowing in opposite directions, yet perfectly separated. This is analogous to the behavior of electrons in topological insulators. These peculiar materials act as insulators in their bulk, preventing the flow of electrons. But on their edges, something remarkable happens. Electrons flow freely, like cars on our quantum highway, immune to obstacles and impurities. This phenomenon, known as the quantum Hall effect, arises from the topological properties of these materials. The electrons are guided by the material's topology, ensuring their smooth and uninterrupted flow. This unique property opens up exciting possibilities for building faster and more efficient electronic devices. Imagine devices where electrons zip along predetermined paths, unaffected by the imperfections that plague conventional materials. The dance of electrons, unveiling Chern insulators. In the ballet of the quantum world, Chern insulators take center stage. These extraordinary materials, closely related to topological insulators, possess a unique twist. Their electrons, when subjected to magnetic fields, choreograph themselves into intricate patterns. This intricate dance manifests as quantized Hall conductance, a hallmark of Chern insulators. The movement of electrons becomes precisely controlled, leading to remarkable phenomena. Imagine a conductor where electricity flows with exceptional precision, unaffected by impurities or imperfections. This is the promise of Chern insulators. Their unique properties make them ideal candidates for applications in quantum computing and spintronics. These fields rely on the precise control of electron spin and charge, areas where Chern insulators excel. Mapping the quantum landscape. The Chern number. In the world of topology, the Chern number reigns supreme. This integer acts as a label, a unique identifier of a Chern insulator's topological phase. Think of it as a fingerprint, distinguishing one topological state from another. Just like the number of holes distinguishes a donut from a pretzel, the Chern number quantifies the twist in the electronic band structure of a Chern insulator. This number dictates the quantized Hall conductance, a direct consequence of the material's topology. The Chern number provides a powerful tool for classifying and understanding the exotic properties of these fascinating materials. It's a window into the topological order that governs their behavior. Fractions of a whole unveiling the fractional quantum Hall effect. In the quantum realm, even fractions can hold profound implications. The fractional quantum Hall effect, or FQHE, a close cousin of the integer quantum Hall effect, exemplifies this beautifully. Imagine electrons, those fundamental particles of charge, teaming up to form quasi-particles. These emergent entities carrying fractional charges behave as if they are entirely new particles. This peculiar phenomenon occurs in two-dimensional electron systems subjected to strong magnetic fields. The FQHE, a testament to the collective behavior of electrons, reveals the emergence of new particles with fractional charges and exotic properties. The FQHE laid the groundwork for the discovery of fractional Chern insulators, further expanding the realm of topological phases and their potential applications. Building blocks of reality, lattice models, and interactions. To unlock the secrets of fractional Chern insulators, we turn to theoretical models. These models provide a simplified representation of complex systems, allowing us to explore their behavior. Lattice models, for instance, imagine electrons hopping on a grid. This simplified picture, though an abstraction, captures the essence of electron motion in a crystal. Interactions between electrons, often neglected in simpler models, play a crucial role in fractional Chern insulators. These interactions, like the social interactions between individuals, can lead to emergent phenomena. By studying these models, physicists gain insights into the intricate interplay of electron interactions and lattice geometry that give rise to the exotic properties of fractional Chern insulators. A glimpse into the quantum world. Experimental observations. Bringing theoretical predictions to life requires venturing into the realm of experiments. Experimental physicists, the explorers of the quantum world, employ sophisticated techniques to probe the mysteries of fractional Chern insulators. Optical lattice systems, where atoms trapped by lasers mimic electrons in a crystal lattice, provide a versatile platform to study these materials. By carefully controlling the parameters of these systems, researchers can simulate the conditions necessary for fractional Chern insulator states to emerge. Observing these states, however, poses significant challenges. The energy scales involved are minuscule, requiring ultra-low temperatures and precise measurements. Yet, the rewards are immense, promising insights into the fundamental nature of matter and the potential for technological breakthroughs. The edge of tomorrow, fractionalization and edge states. Fractional Chern insulators, like their integer counterparts, harbor secrets at their edges. These edges, far from being mundane boundaries, host exotic excitations known as edge states. Imagine a dance floor where dancers at the edges move in a coordinated fashion, their movements dictated by the music. Similarly, electrons in edge states flow unidirectionally, their motion governed by the topological properties of the material. But here's the twist. These edge states can carry fractional charge, a consequence of the fractionalization phenomenon. This fractionalization, a hallmark of strongly correlated systems, has profound implications for quantum computing, where information can be encoded and manipulated using these exotic states. Quantum leaps and bounds applications and future directions. Fractional Chern insulators, with their peculiar properties, hold immense promise for technological advancements. Their potential applications span diverse fields, from quantum computing to spintronics. The robust edge states, immune to disorder and imperfections, offer a pathway to building fault-tolerant quantum computers. These computers, leveraging the principles of quantum mechanics, could revolutionize fields like medicine, materials science, and artificial intelligence. Moreover, the ability to control and manipulate fractional charges opens up new possibilities for spintronics, a field that aims to use electron spin, rather than charge, to store and process information. The journey into the world of fractional Chern insulators is just beginning. As researchers delve deeper, unraveling their mysteries, we can expect even more exciting discoveries and applications to emerge. Tools of exploration, methodologies, and techniques. Exploring the quantum realm requires specialized tools and techniques. To study fractional Chern insulators, physicists employ a range of sophisticated methods, each offering a unique window into their behavior. Numerical simulations, for instance, allow researchers to model these complex systems on computers, providing insights into their properties and behavior. These simulations help to bridge the gap between theoretical predictions and experimental observations. Experimental techniques like angle-resolved photoemission spectroscopy, or ARPs, and scanning tunneling microscopy, or STM, provide direct probes of the electronic structure and excitations in these materials. By combining these powerful tools, physicists continue to push the boundaries of our understanding of fractional Chern insulators and their potential applications. Case studies: fractional Chern insulators in action. The theoretical and experimental advances in fractional Chern insulators have led to exciting case studies, showcasing their unique properties and potential applications. One such case study involves the realization of a fractional Chern insulator state in a lattice of ultra-cold atoms. This experimental breakthrough, achieved by trapping and cooling atoms to incredibly low temperatures, provides a powerful platform to study the interplay of interactions in topology in a highly controlled environment. Another promising avenue involves using fractional Chern insulators for topological quantum computation. Researchers are exploring ways to encode and manipulate quantum information using the robust edge states of these materials. These case studies, representing the forefront of research in this field, highlight the remarkable progress made in understanding and harnessing the exotic properties of fractional Chern insulators.